This is the 555 timer unpacked, an ACE's deep dive into how the 555 timer actually works internally. The 555 timer is an integrated circuit that can operate in two main modes. In astable mode, it produces a continuous square wave oscillation, and in monostable mode, it produces a single timed output pulse when triggered. One of the most important internal circuits of the 555 is the SR latch, also called a set-reset latch, which stores one bit of data. SR latches can be built using either NOR gates or NAND gates. A NOR gate-based SR latch is active high, while a NAND gate-based SR latch is active low. The 555 uses the NOR gate latch, which is why this project implements it. When the set input goes high, the output Q is driven high, and the complementary output inverse Q goes low. Further set inputs don't change anything because the latch holds its state. When the reset input goes high, the opposite happens. Q goes low and inverse Q goes high, and it stays that way until a new set input arrives. The latch works by connecting the outputs of the two NOR gates into the inputs of the other. This creates a bistable feedback loop. When both inputs are low, one side will resolve to high and the other to low depending on the previous state. But if both inputs are driven high simultaneously, both inputs go low, creating an invalid condition where the next state cannot be predicted. Another key component inside of the 555 is the pair of op-amp comparators. An op-amp comparator outputs a logic high when the non-inverting input is at a higher voltage than the inverting input, and a logic low when it is lower. Inside of the 555, these comparators monitor the voltage across the timing capacitor and decide when to set or reset the latch. Inside the chip, there are three 5 kilo ohm resistors connected in series, forming an internal voltage divider. This divides the supply voltage into two precise reference points. 1/3 of the source voltage, approximately 1.66 volts in our case, and 2/3 of the source voltage, approximately 3.33 volts. These reference voltages are fed to the two comparators. The upper comparator compares the timing capacitor to 2/3 of the source voltage. Its non-inverting input receives the capacitor voltage and its inverting input is tied to the 2/3 source voltage. When the capacitor voltage rises above 2/3 of the source voltage, the upper comparator outputs high, resetting the latch. This activates the discharge transistor, which pulls the capacitor towards ground, and the LED connected through the NOT gate goes high. The lower comparator compares the capacitor to 1/3 of the source voltage. Its inverting input receives the capacitor voltage, and its non-inverting input is tied to the 1/3 source voltage. When the capacitor voltage falls below 1/3 source voltage, the lower comparator outputs high, setting the latch and turning off the discharge transistor. In astable mode, the timing components R1, R2, and the capacitor control how quickly the capacitor charges and discharges. R1 and R2 determine the charge time, while R2 alone determines the discharge time through the transistor. Because the comparators trigger at 1/3 source voltage and 2/3 source voltage thresholds, the capacitor repetitively charges between 1.66 volts and 3.33 volts, then discharges back down, repeating the cycle. This process produces a continuous square wave output at the 555 output stage ranging from 0 to 5 volts. This is the 555 timer creating a 2 kHz output on a passive piezo buzzer. For a piezo crystal to make a sound, an oscillating voltage must be used. On an active piezo buzzer, it creates its own oscillation, but frequency is not controllable. On a passive piezo buzzer, frequency is controlled by the input oscillation. To achieve 2 kHz, R1 is a 100 ohm resistor, R2 is a 330 ohm resistor, and C1 is a 1 microfarad capacitor.